Welcome. Good evening. I want to tell you a story with ancient giants and lurking monsters. A story of catastrophe, marvels, and extinction. And our tale begins in the Great War with Karl Schwarzschild, no longer a young man, serving in the German army on the Eastern Front when he hears news of a breakthrough. Albert Einstein and David Hilbert have discovered an entire new way of looking at space and time and gravity that will revolutionize our understanding of the universe, the theory of general relativity. This is November 1915. The next month, December 1915, Karl Schwarzschild of the Eastern Front discovers the first exact solution to the complicated equations of this theory, the Schwarzschild solution. He has also fallen seriously ill and is sent home, where he dies in May 1916, half a year after his discovery. But his solution, the Schwarzschild solution, lives on, turns out to describe non-rotating black holes and be central to our understanding of general relativity. It's almost 50 years before this solution is generalized to include rotating black holes, completing the description of those black holes that are relevant for cosmology and astrophysics. And initially, these solutions are considered to be some exotic curiosities with little relevance, perhaps, to the real world. But that changes. And now black holes have taken a central road at the crossroads of astrophysics, cosmology, general relativity, and the search for quantum gravity. And today I'm happy to try and share some small part of the fascination of this object with you. There will be some questions at the end, but I would also like to encourage you to ask questions if something is unclear about the stuff that I'm talking. If you have questions about the thing that I'm saying at the moment, then just please interrupt me and ask questions. So let's begin with what black holes are. And there are regions of space-time that are so strongly curved that there's no way out of them. So let me explain what that means. So, according to general relativity, mass curves space-time. So, for example, the sun curves the space-time around it, and that's why the Earth is not going straight along a line. So, if you think that the Earth is going, up in time, it would be always in the same position, just move straight line up in time. But because of the sun, it's instead going on in this corkscrew, which, if you think about it, how it's moving in space, looks like it's going in a circle, but in fact, it's rising up like this. And the bigger the mass, the bigger the curvature. And when you have a big enough mass in a small enough space, the curvature becomes so large that these trajectories curve so that you cannot get out. And it's not a question that, you don't have enough force to escape. It's literally that there is no route out from the black hole. And black holes can be created by just taking mass and putting it inside a small enough radius. It actually doesn't matter how much mass you have, it's just any amount of mass as long as you press it small enough. So if you take the entire mass of the Earth and press it inside a ball of radius of about 9 millimeters, then you will get a black hole, a rather small black hole. If you take the sun and put all of its, want to make a black hole, then you have to compress all of its mass inside 3 kilometers. This radius is called the Schwarzschild radius. And so the mass of the black hole is always proportional to its radius. So if you know the mass, you know how big it is. And black holes have many fascinating properties. I mean, probably tens of thousands of scientific articles have been written about them. But they're also extremely simple objects at the same time. So if you tell me the mass of a black hole, how fast it's rotating, and what is its electric charge, which for astrophysical black holes is negligibly small, then I know everything about the black hole. So these, black holes with these same three numbers are like Tolstoy's happy families. They are all alike. So if you take two stars, stars are very complicated. They have all kinds of internal structure and, lots of processes happening inside. So you take two different stars, push the matter small enough, and if they have the same mass and same rotation and same charge, then the result is the same. So a lot of information is lost in black hole collapse, or maybe lost. This is an issue that is not entirely understood. So the most characteristic feature of the black hole is, of course, the surface. So this is a point of no return, a final border beyond which no one can return. And sometimes this is called an event horizon. Now, how many have heard the term event horizon? Most people probably. So this is the boundary of the region we can see. So of course, if we think about horizon, like if you're at sea, then it's the limit to which you can see. It's called an event horizon because we cannot see inside the black hole. A better term used for that is a trapped surface. How many have heard the term trapped surface? Some people. But it's basically just a different way of looking at the same thing. So instead of looking what can an observer somewhere see, just looking at what's happening on the surface, and the surface is trapped if light can travel only in one direction. So light can go in, but not out, and if light cannot get out, if there's no route for light out to get out, then there's also no route for anything else. But strange things can also happen when you come near a black hole, not just when you cross the trapped surface. And this is related, one of them is related to the fact that gravity affects, so I had this term space-time. So it affects how objects move in space, but it also affects how they move in time, how fast they move forward. Because in general relativity, time moves differently in different locations, and in places where you have more mass, where the space-time is more curved, time moves slower. So this is something that has been, not only something that has been observationally confirmed, but it's also relevant for our daily lives. So if you think of the global positioning system satellites that are 20,000 kilometers up, they experience a weaker gravitational field than us on Earth because we are closer to the mass of the Earth, so the space-time is more curved here. And for them, therefore, time passes 38 microseconds a day faster than for us on Earth. Our clocks pass slower. Now you may wonder why I said this is relevant for your daily lives, because even if you are very busy, probably 38 microseconds is not going to ruin your schedules for one day. But the GPS positioning system is based on radio waves, which travel at the speed of light, which means that in 38 microseconds they travel 10 kilometers. So you have satellites, on different parts of the sky, and then they send radio signals with timestamps, and you get those radio signals and you compare those timestamps. So basically, you know when they send the signal, you know the trajectory, you know when you receive it, so you can conclude where you are based on how long that light took to reach you. And 10 kilometers, so if you try to, if you try to locate the DS building where you're coming to with GPS, then 10 kilometers is a rather serious mistake. Now, so for the Earth, nevertheless, like in absolute terms, 38 microseconds per day is quite small, and this is true everywhere in the solar system, even on the surface of the sun, where gravity is strongest in the solar system. But for black holes, this time slows down without limit as you approach the trapped surface. So if you, for example, let's say you go to the closest black hole, which is about 1,600 light years away, you take your spaceship, and then you go down close to the trapped surface, and then you come back up, and 1 minute has passed for you, then 1,000 years can have passed for others. And of course, when you go closer and closer to the trapped surface, then you can extend this infinitely, so maybe 1 million years have passed or something. So in Irish folklore, there are the hollow hills, where, if you go into them, you pass into the other world or the fairy world, and it may be that you spend the time there and a generation has passed when you come back. But with black holes, you have to be careful. It's not enough that you don't enter, you also shouldn't get too close. So we are all traveling in time, but in forward. So if time can move differently at different rates in different locations forward, we can ask the question: is it possible that time somewhere can move backward? And the simplest example of this in general relativity is in fact provided by this rotating black hole solution discovered by Roy Kerr in 1963. So if you take, the recipe is simple. You take a rotating black hole and you go down very close to it, you rotate counterclockwise, you return, and you can come back up before you left. You don't need to do this at midnight or on Samhain, so any time is okay. If you look at the solution that Kerr found, it looks like you can do this. In fact, this doesn't actually work. The problem is just that in order for there to be a route backwards in time, the hole has to spin very, very fast, the black hole. In fact, the trap surface disappears. So I'm not sure if one should call the black hole because it's not actually black. But anyway, this solution is unstable, which means if you go in, you will destroy this black hole, this object, before you come back up. And of course, realistically, you couldn't form it because there's always some disturbances in the universe. Nevertheless, time travel is actually a very common feature of solutions of general relativity. And not all of these solutions are unstable. So if you just take something that is compact enough and is rotating fast enough, and you go counterclockwise, then you're mixing space and time, and you can go into the past. So the idea is basically that time moves differently in different directions in different places. So instead of going like this, you go like, and then you cross back. It is not known whether this actually happens in reality. All of those solutions are pretty exotic, and we can't make black holes or similar very fastly rotating objects. So it may be that this is actually outside the domain of validity of general relativity. So general relativity is not the final theory of space-time, but we don't yet know what lies beyond it. And some people, like Stephen Hawking, suggested sort of a chronology protection conjecture, stating that actually the completion of general relativity, the more general theory, will forbid this, but we don't know. So this is all staying outside. What happens if you go inside? One suggestion that has been made that you may be familiar, who is familiar with the idea that black holes are routes to other universes? Refreshingly few people, thank you. But this idea is actually based on physics. Again, if you take this rotating solution found by Roy Kerr, then what happens, and then the natural way to look at that solution is that if you go into the black hole, then you enter another universe, so you have another outside. So, if you enter the hollow hills, you go into the other world. Probably, however, this is not true for real black holes, because this happens for black holes that are eternal, undisturbed, and so on. And you take into account the real black holes have formed at some time, and there's other stuff in the universe, so probably this is not the case, but we are not entirely sure. More reasonable possibility is that because the black hole has formed at some time, so there has been some matter, when the black hole forms, the matter falls into the center, the density becomes infinite, it's called the singularity, and then general relativity stops. Like, we don't know what happens then. So we would need a more complicated, also more complicated, but let's say more sophisticated, more fine-grained theory of gravity to understand the insides of a black hole. And there are many proposals for what happens. Loop quantum gravity, string theory are proposals for quantum gravity, and they each have their own explanation of what goes on inside black holes. But rather than talking about these theoretical possibilities, I want to discuss the reality of black holes. Because this is where the black hole, like we are living in the golden age of black holes. And this is not because of work of theorists, I mean, I'm a theorist myself, but really because of advanced observations. So the black holes are born when something greater than humans die, that is to say, stars. So to simplify a lot the very complex processes of stellar evolution, stars have nuclear fission in their center because the density is so high. This generates pressure that stabilizes the star. When the nuclear fuel runs out, the star collapses. And if it's massive enough, more massive than about 10 times the mass of the sun, then this matter will be pushed inside the Schwarzschild radius, and a black hole is born. So stars are very common in the universe, as you can see just by looking at the night sky. This means that black holes are also very common. So black holes are not some exotic, rare objects that may or may not exist. They're something that are ubiquitous in the universe. I know I probably mangled that word. So. But they're difficult to see. Like if you take a black hole of 10 solar masses, then the Schwarzschild radius is 30 kilometers. So if it's somewhere far away from us at astronomical or cosmological distances, 100,000 light years or something, it's very difficult to see these objects. But we have seen black holes even 1 billion light years away from us, and the most detailed observations are due to gravitational waves. So now I should explain what are gravitational waves. And there are small ripples in space. So when I raise my hands, the moon comes a little bit closer. I didn't actually check if moon is upon the sky, and otherwise otherwise I'd reach down if it's on the other side. Because of the gravity of my hands. Of course, there's not a lot of mass in my hands, so the effect is quite small, but it's real. But the information that my hands are now up moves at the speed of light, so it takes 1 second to get to the moon, 8 minutes to get to the sun, and so on. So whenever I move my hands, I'm causing these ripples in space that send a signal of where my mass is. Like you can think that if you're in water and you move about and you cause waves, and if someone can't see you or hear you, if they can only see the waves, then they will only notice that your location is different when the waves reach them, and then from the shape of the waves and the way the waves move, they can, figure out where you have been and how you're wiggling your hands and feet. So gravitational waves, to simplify a complex phenomenon, is basically the same thing. So you have these little compressions and extensions in space, these waves in space, that any mass that moves creates. But most of them are, and the nice thing about them is that they travel almost unchanged through the universe. So unlike light, which is absorbed and scattered, then gravitational waves basically almost don't interact with matter at all. So you can see them from any distances, but they're very, very weak. So you need very powerful disturbances to see the gravitational waves. And now we get back to black holes, which are actually the topic of this talk and not gravitational waves. So, because the most violent events we know in the universe are those of collisions of two black holes. And September 14, 2015 was a historic day. This was the day when humanity, for the first time, measured gravitational waves in the laboratory. So the LIGO team, with 2 of its detectors in the United States, and there's also one detector called Virgo in Italy, detected gravitational waves that were created when 2 black holes of about 30 solar masses orbited each other and merged about 1 billion light years from us. So this happened 1 billion years ago because the gravitational waves, which travel at the speed of light, took 1 billion years to reach us. And the Nobel Prize was given very quickly in 2 years for this discovery. So here is a simulation of this collision. So this is a similar kind of event that was seen. So in here, which unfortunately you can't see, but is the gravitational wave signal. So this is just a wave with where you can see where you could be able to see. So how the frequency and the amplitude of the wave are changing. And here you have 2 black holes that are orbiting each other, and this is the time in seconds before the collision. So the black holes, and now we're zooming in, and these are gravitational. So this is the distortions in the space-time, the space-time curvature that you see. So the black holes are orbiting each other, just like the Moon and the Earth are orbiting each other, and when they orbit each other, they send off gravitational waves, so they lose energy, so they come closer, move even more rapidly, so they send even more gravitational waves, and this sort of a relationship dynamic is very unstable. So they orbit each other, come closer, And if these were isolated, they would be Schwarzschild black holes, so they would be completely spherical. And now we are measuring 1/1000th of a second. When you start already a bit seeing that these are not completely spherical, they get distorted, come closer to each other, and merge, never to be separated. So then the black hole undergoes this ring down, and then quickly, in a 100th of a second or so, settles to this final solution that is described by the this solution called the Schwarzschild solution that he discovered in December 1915. And this is simulations by the Simulating Extreme Spacetimes Project, SXS. So they have a number of videos of these black hole collisions on YouTube, if you want to have a look. Since then, we have seen well over 100 gravitational waves, mostly from black hole collisions. So here, so this is the mass in units of solar mass, which you can't see, but basically these are in few solar masses to about 200. So this is, for example, like 5 solar masses, 10 solar masses. So these are the progenitors, and then you have the mass of the final black hole, which is not the sum of the two, because these radiate so much gravitational waves that they lose energy, and so the mass is smaller. The essential thing about this is that we see, first of all, that we've seen a lot of them. And actually, now you see a few times a week. You can even get an app that will tell you, oh, gravitational wave just passed through the Earth. Another thing is that these masses are from a few solar masses to a few hundred solar masses. So then becomes the question how these grow. I mean, here we see a bit of the growth, because we see black holes coming together and merging. So black holes grow by eating each other. Maybe this is an appropriate metaphor if one of them is very small. If they're of the same size, I think we should have another one. And by eating their neighbors. So any material that is in the vicinity that falls into the black hole will go through the trap surface and never return. But in addition to and so we understand more or less how you form these black holes of masses, 50 solar masses, 100 solar masses. But there is a problem. That we see in the hearts of most galaxies, black holes whose masses are millions to billions of solar masses. And this black hole, nevertheless, typically they're a small part of the total mass of the galaxy, like in the case of the Milky Way, about 1/1,000,000th of the mass of the Milky Way is in the supermassive black hole in the center, but their evolution is closely tied to the evolution of the galaxy. And it seems quite difficult to understand how they have actually grown so large, so fast. These have become very prominent recently. So 4 years ago, 1/2 of the Nobel Prize in Physics was given to two teams, that of Reinhard Genzel and that of Andrea Ghez, because they had discovered, starting in the 1990s, this Milky Way central black hole, the mass of which is about 4 million solar masses. And about half of the prize, not about, exactly half of the prize, was given to Roger Penrose for showing what I mentioned earlier, that if you just take enough mass and press it inside a radius, then you will form a black hole. And he showed really mathematically rigorously that this is what happens. This is visualization of data taken by the group of Andrea Ghez. So everything marked S here is a star. This is looking at the center of the galaxy. This white thing here is something that we don't see. It's the center of the mass where we don't see anything. And this is the year on which we have the data. I'll put it running soon. And this resolution is such that this is about 1/10,000th of a degree. So if you use this telescope that they used to look from Dublin to New York, the resolution would be about 1 meter. So you could see individual people walking about on the street. And if we put the simulation on, there's a bit of a delay. No. Yeah. So here you see as the years move forward, the stars move. And from the motion of the stars, you can infer the mass of this object. You can also measure how it's rotating. And you see that this 4 million solar masses, and then you have this innermost orbit here of this particular star, which passes very close to the mass. So you know that this cannot be a cloud of gas, it cannot be a group of stars or anything, first of all, because you don't see any light, and also because this object doesn't slow down, it's just responding to one mass here. This orbit passes within about 1,000 Schwarzschild radii, which is already very compact, and actually you also see some light coming from about 3 to 5 Schwarzschild radii next to the mass. So you know that it has to be very small, and from that and from the orbits, it was concluded that this is a black hole that's holding these stars here that cannot escape and perhaps will in time fall into the black hole. This instrument did not have resolution to see what's happening precisely there, unlike the Event Horizon Telescope, which published this picture of galaxy M87 center in 2019, and this picture of the Milky Way in 2022. So the resolution of this instrument is about 1,000 times better. So if you looked with this from Dublin to New York, you could make out the pores on the face of the people in New York. So what is shown here, this is looking at the center of the Milky Way, and no wonder I said that black holes are black, so what's this light? So this is matter that's orbiting the black hole, so it hasn't fallen in because it's rotating, just like the Earth doesn't fall into the sun because it's going around. And this matter rotates almost at the speed of light. It's very hot, and we are seeing the light or the X-rays emitted by this matter as it's rotating. The rotation disk is tilted, so here it's where the matter is coming towards us. That's brighter. Here it's going away. The rotating matter is actually much sharper than these images. Unfortunately, the resolution of this telescope, which is an interferometer, so it uses telescopes in different parts of the Earth. So it's basically a telescope the size of the Earth. Unless you go to space, you can't make any bigger. But the resolution is not quite enough to resolve the details. So these look a bit fuzzy just because the resolution is about this width. And here, the event horizon is a bit smaller than this black area. The black area that you will see is always a bit bigger because if light is passing even close to the event horizon, it will actually get captured by the gravity of the black hole. So you will never see quite to the event horizon. But these are very close-up pictures of these trap surfaces and of the two gigantic black holes that we see. So this is 26,000 light years away, the Milky Way, center of the Milky Way, and M87 is 55 million light years away. They're about the same size on the sky. So if you look at the sky, these pictures are about comparable because this is about 6 billion solar masses. So it's 1,000 times, about 1,000 times further away, but also 1,000 times bigger. So these are single black holes. Some of them come in pairs, just like these solar mass black holes that I showed. So, and these we have not seen yet, like we predict theoretically that they should be there. We haven't seen any of them. It's actually, we are very lucky that we have instruments that can see this, but in the vicinity there are no other black holes, the supermassive black holes whose size would be large enough and distance would be short enough that we could see them. There are basically only two, unless you have a telescope bigger than the Earth, so if you go to space. But even if we don't see them, we can hear them. And there are some recent observations, especially better observations last year, of things that are called pulsar timing arrays. So the idea is that we are here on Earth, and then we have pulsars that are rotating neutron stars on different sides of the sky. So the idea is that you have a neutron star that sends a signal, and because it's rotating, sometimes we see the signal and sometimes we don't as it's rotating. This is like a lighthouse. And these pulsars are extremely stable. So you see this tick, 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 tick. So they're very precise clocks. I've actually heard the proposal that we should replace our unit of time, definition of the unit of time to be defined with these pulsars. But I think atomic clocks are still better. So the idea is that you see these ticks from different parts of the sky. So you listen to them, and then you hear disturbances. So they're a bit out of tune. And they're out of tune in a way that is correlated across the sky and says these things cannot communicate with these things. How are we going to send these signals? It has to be something that's close to the Earth. And the best explanation for the observations is that there are gravitational waves passing through the solar system, and therefore they affect how we see this, how we hear these pulsars. So this is not yet a detection by physics standard, but it's getting very close to a detection. Probably in a few years it will be announced that there is a detection of gravitational waves by this route. So these are basically then generated by many of the supermassive black hole pairs that generate gravitational waves that are sweeping through us. The next step is the satellite called LISA, for Laser Interferometer Space Array, project by the European Space Agency ESA, supported by NASA, which is set to fly in about 10 years. Usually these are always late, but actually the schedule has been moved forward recently. So this is a satellite that will fly from Earth to space, and then it will co-rotate with the Earth around the Sun. It's 3 satellites, and it will measure these small disturbances in space-time, gravitational waves, and it will see gravitational waves from these supermassive black hole pairs. So I showed you the simulation of solar masses, of these 30 solar mass black holes, and LISA will see these gravitational waves generated by central black holes of million solar masses to a billion solar masses. So what happens is that you have 2 galaxies, both of them are central black holes, then the galaxies meet, they merge, and these central black holes come together, orbit each other, and then they finally merge. I mentioned that there is a problem in explaining how these supermassive black holes have actually formed. And the problem is that we have seen them now already when the universe is 500 million years old, which is a lot of time for you and me. But for black holes, it's not. It's quite a short time. And new observations, especially by the James Webb Space Telescope, launched in 2021, have seen more black holes, heavier black holes at earlier times. And we don't really know how to form them. There are various ideas. One possibility that I have worked with, this is the only part of this talk, by the way, that's related to stuff that I actually do, is that they're seeded by primordial black holes. So that it's possible to have black holes that are older than stars, that are not formed in stellar collapse and then create matter, but instead are formed earlier. And it's also possible that these same kind of primordial black holes can explain what is dark matter. So most matter in the universe is not made of the things that we are made of. We are made of protons, neutrons, and electrons. So 80% of the matter in the universe, this is not true. We have seen this matter only by gravity, so we see how it bends light, we see how it affects the motions of visible matter. So looking at the universe is like looking at a Christmas tree in the dark. So you see only the lights, the visible matter, but the bulk of the mass is in the tree. And it's possible that this dark matter consists of invisible particles, which you may think fanciful, but we have hundreds and hundreds of different models for that. Or it may consist of black holes, which we just haven't seen because they are so small. So now to make black holes, as you know, all you need to do is take mass and push it inside a small enough radius, and then you have a black hole. So to make a primordial black hole means that at early times, you need to have very large mass concentrations just in some rare regions. It's enough that will then collapse to form the black hole. So basically, in the early universe, matter is typically very uniform, but you need to have these mountains, these very, very high concentrations of mass in the primordial universe. And these can be they can be dark matter, or they can form the seeds around which the black holes in the centers of galaxies grow. So you can jumpstart the growth process just by having this big black hole that then accretes matter. Then the question is, how can we be sure which is which? How do we know if dark matter is black holes or particles? How do we know whether these black holes in the centers of galaxies are seeded by these primordial black holes or not? One way is to look at, again, something passing between our line of sight, but now not to pulsars, but to stars. So we sit on Earth and we look at stars in the Magellanic Clouds, or in the Andromeda galaxies, on the nearby dwarf galaxies or galaxies. And then if a black hole passes between us and the star, then their gravity bends the light, so it becomes a bit brighter. So there's extra twinkling of stars, called microlensing. This is not seen. So this means that if dark matter consists of black holes, they have to be so small that they don't markedly affect the light from stars. That they wouldn't cause any of this twinkling, which means their mass has to be below the masses of, they cannot most be at the same mass as the asteroids in the solar system, which by the way means that the physical size is tiny. So recall that if you have solar mass object that turns into a black hole, the size is 3 kilometers. Asteroid mass, which is typically between 1/100th of a billionth and 1/1,000,000th of a billionth, gets very difficult with these millions and billions here. Solar masses, then the size is, the biggest ones are the size of molecules, and the smallest ones are smaller than atoms. So there's no way that you will see them accrete matter or something. Everything is way too small, but you might see this twinkling. So what if they become very small? And now we actually come to the question of what happens to black holes. Are black holes forever? I just told you that two black holes collide, they will never separate. So what's the fate of black holes? Stephen Hawking predicted that black holes evaporate by what is now called Hawking radiation. So nothing can come out of the black hole, but the black hole trapped surface itself radiates particles, so it's sense of energy, so the black hole loses mass. And ordinary objects like a kettle, if a kettle is hot, it radiates heat and it gets colder. Not so for black holes. When black holes radiate, they get hotter. So this means that they get smaller, so they radiate even more, they get even hotter, and so on. So the smaller the mass, the bigger the temperature, and so black holes evaporate away in a finite time unless there's something to stop the evaporation. So the final stages of this black hole evaporation are very strong. You have this very strong radiation pulse, and again, this is something that is not seen. So this means that black hole masses cannot be smaller than the asteroid mass. So, if they're heavier, the radiation is so weak that we wouldn't have detected. Which basically means that the asteroid masses are the only possibility, except, and this I find particularly interesting possibility, except if black hole evaporation stops at some point and leaves a relic with a mass of about 1 microgram, in which the remnants of primordial black holes with mass of 1 microgram could be all of the dark matter. So black holes are literally central to galaxies. They're crucial for gravitational wave astronomy, which allows us not to only understand black holes better, but also understand the theory of general relativity better, because we can measure how the space-time is curving when these black holes are orbiting each other. We can compare that to observations. We can use gravitational waves sent by black holes to understand what's happening in the universe. And some primordial black holes, either those at the centers of galaxies or in or those that form dark matter, may hail from ancient times. And now you may ask, so how do you actually form these primordial black holes? What gives you these mountains? And that's actually what I'm working on, but that would be a whole another story. So let's leave it for another year. Then we can, if you look from these ancient times to the future, after lengths of time that are, I think, quite difficult to intuitively understand, although you can write down the zeros. Stars die out. So stars collapse into a black hole, and then they cannot come back. Of course, not all stars form black holes, and material from stars then goes out, forms new stars, but you lose material every time. Nuclear fuel keeps running out, and the peak of star formation is already past. And eventually, no new stars will be formed. Eventually, also galaxies disperse. Galaxies are not stable; they're just very, very long-lived. Finally, the only light will be the faint evaporation from black holes that lights up the darkness until it too fades. And if this seems like a melancholy end, you may reflect on the fact that when this happens, all of humanity will have gone the way of Karl Schwarzschild and become extinct. So there is no one left to grieve in the darkness. And on this note, I wish you a serene Samhain and open up for questions. Thank you.